All right, so now we are in the circular weight. Yeah, circular weight. Okay, so for the circular weight, there exists at P0, P1, P or all the P, yeah, of weighting processes such as P0 is weighting for a resource that is held by P1. P1 is waiting for a resource that is held by P2 and so on. And then is waiting for resource that is held by Pn, and Pn is waiting for a resource that held by PO, and so on, so forth. Yeah. So this is the what we call this is a deadlock characterization. There are how many? One, two, three, and also circular weight. Altogether, 4 conditions. Yeah, 4 conditions. So resource allocation graph, RAG. A set of vertices, yeah, V, and set of edges, E. V is partitioned in 2 types, yeah. So where P1, P2, and Pn is representing the processes, the set consisting of all the processes in the system. And R representing all the resources, resources type actually in the system. So different resources, different, just now you can see how many instances. So that's why they say resources type, yeah, resource types. Okay, we use R for the resource type. So, and then request H, which is this PI request or directed H to the PJ, for example. Yeah. So assign H. So we are using the arrow also. So RJ will assign to PI. Okay, this one assign H, request H, and then assign H. Yeah. All right. So if I not okay, before I forgotten something, because resource allocation is representing the processor, the methodology, the algorithm, representing how we want to develop the algorithm to represent. So we use this graph, yeah, resource allocation graph. So process, okay, we can see process is like this circle, yeah, this circle, solid circle. And resource type with 4 instances, we representing by this rectangle or square, yeah, with the 4 instances, which is a small square, yeah, in the box or in the square, for example, like this picture, yeah, or diagram. PI request instances of RJ. So this is the RAG just now to represent this. Yeah. Similar to P is holding an instance of R. So they will represent this using this diagram. Okay, RAG. This is RAG. Yeah. All right. So next, so type of H, we have this request H. PI request to this resource. Yeah, P1 request resource R2. So request H, this PI request resource to RJ. Yeah, PI request. Yeah, all right. And then this one for assign. Yeah, for assign, similar, right? Okay, very clear. And then example of resource allocation. This is the example. Okay. Okay, example of the, resources. And then we have these processes, how they assign, how they request. Okay, this is kind of the example of the graph. graph. What is the name of the graph? Resource allocation. Yeah, resource allocation graph. All right. For example, okay, we have this example. Yeah, we have four process P1, P2, P3, and so on. We got resources. Yeah, so just we can play this. Okay, play this. Okay, when you play this slide, you can we will explain. Okay, instead of we write, we just explaining this through a diagram. Yeah. Okay. And next, like this. Okay. So we have done this. And then this one, set of P. We have P1. It's very straightforward. E. Okay. Is a request. This one R. R is resource. This one is the H. Okay, is the H. All right. So this is the set of P, R, and E. Yeah. Basic facts. If a graph cycle, if a graph contains no cycles, means no deadlock, of course. If a graph contains a cycle, yeah, and if only instant per resource type, then deadlock exists. If several instances per resource type, then possibility of deadlock. Okay. So okay, this is graph, yeah. And then is there a deadlock? Based on this diagram, yeah, based on this diagram. So resource allocation graph with a cycle. Okay, this one, because of course there is a deadlock will happen. Because back to this concept. If there is a cycle, yes, there's a deadlock. Okay, this is array G, example 2, several instances of resources. Okay. There are two cycles. Okay, they're explaining this P1 to R1, P1 to R1, okay? P1 to R1 here, yeah, this. And then P, after that R1 to P2, okay? This one, another request, and there's a request, and also there's a, this one ages, right? Age, resources, some requests, okay, this is, please check, yeah, that one. So very straightforward. Okay, this one. Try to understand this. So the cycle, first cycle is this. First mentioned. Okay, this is first scenario for cycle. We got two cycle or two scenarios like this. Okay, for example. Yeah. So P1, P2 are in the deadlock step. Finally, P1, P2, and also P3 are in a deadlock state. When we have these two cycle. Yeah. So now, yeah. Okay, is there a deadlock for this? Okay, this allocation graph with a cycle. Okay. Through this one, if you check this properly, yeah, and then P1 pass and then P3, and then okay, this, and then here, we will keep on waiting because they are requesting here. Then is there a deadlock? So, of course, there's a deadlock. Yeah. Okay, this scenario. Yeah. All right. So example 3. Okay. The array G has a one cycle. P1. okay, request to R1 resource, and then process P1, and then after that P3 this request, and next P1 request, and then R1, okay, to P2, and then after that P3 request to R2, and R2 okay, release to P4, yeah, give to the P4, yeah, all right, and yeah, okay, and then P2, finally P1 and P3 are in a deadlock state, okay, all right. So however, the system is not deadlocked when P4, yeah, when P4, okay, you say that when P4 release R2, this resource can be assigned to P3. Yeah, okay, all right. And next, so P3, however, the system is not deadlocked when P4 release P4. Where's the P4? P4 here. P4 release R2. This resource can be assigned to P3. Okay. So after that, no more cycle. So that's the things. Yeah. All right. Handling a deadlock. First, ensure that the system will never enter deadlock state. Yeah. Deadlock prevention and also deadlock avoidance. Yeah. And second, allow the system to enter deadlock state and then recover. We can do that as well. Or the third, ignore the problem and pretending that deadlocks never occurred in the system. So now this technique used by most operating systems, including Unix. Okay, can be. All right. So this is a method for handling deadlocks. Okay, I'm not sure. Recent, maybe there is a new changes and so on to improve that. Yeah. Okay. Depend on the architecture, depend on the type of the application that we're going to apply. Maybe different kind of the application, it will reflect this because the process is different. You see, especially for requesting a resource, assign a process to release. So that's why there is a scenario that pretending that deadlock never occur. I can say it will because of the system itself. Okay, the type of the applications, the flow, we are different flow, but not system is the same. That's why when we develop, we have to do some what we call this as a requirement analysis. We say that some requirement criteria when we had to do literature review. We need to understand the requirement of the system. So actually, all systems, even system pendaftaran, for example, register system, okay? System of the for the student. Different system could be different process, different flow. That's why, okay. So even the name is system is the same, but the process, the flow, the architecture, the resources, they are different. That's why this, I mean, analogy, it can be a true. Yeah, it's possible. Okay, because the system is not all same. Okay, that's why we cannot say that this technique is belong to all. That's why. Yeah. So on specific type of the application. So that's a true. Yeah, this statement. All right. So method for handling. So now you can see they do some reviewing the technique for handling. So this is like kind of the literature review that method of handle deadlock. We have prevention, we have avoidance. Okay, in future, how lots of things. So when we do for same like our assignment that we are looking for the technology current in whatever techniques, especially in the operating system. Yeah. So recovery, ignore, for example. Okay, this is the things. Yeah. So avoid above from apple at the same time. Yeah. So you can see RAG here, and then we have a banker's algorithm. So until now, maybe because I don't know, because within 5 years we can see method to handle deadlock, for example. Yeah. All right. So back to here, avoid above from happen at the same time. So if fail any of these four conditions simultaneously arise during a deadlock, one mutual, previous chapter, yeah, we have mentioned this, pull and wait, no preemption, and also circular wait. Okay. All right. So now process termination and then process. Okay, there is a word of recovery here. Okay, if fail any of these, so we need to recovery. See, recovery by process termination or resource preemption, preempt that process, release, give to another. So this okay, maybe could be more. I also doesn't know. Within 5 years, maybe you can check within 5 years from now to 5 years back. Maybe. Yeah. All right. So deadlock prevention. So we are talking now regarding deadlock prevention and ensure that at least one, at least one of the necessary condition for deadlock does not hold. Can be accomplished restraining the ways requests can be made. First, mutual exclusion. Next is hold and wait. Mutual exclusion must hold for non-shareable resources that can be accessed simultaneously by various processes. Therefore, cannot be used for prevention. Yeah. And for the wait and hold and wait, must guarantee that whenever a process requests a resource, it does not hold any other resources, which means that require process to request and be allocated all its resources before it begin execution or allow process to request resources only when the process has none allocated to it. And also low resource utilization. And then at the end, starvation mean will happen. Okay, starvation possible. So this scenario will happen because of the low resource utilization. Yeah. So no preemption, not practical for most of the system. Okay, not practical. If a process that's holding some resource request another resource that cannot be immediately allocated to it, then all resources currently being held are released. Preempted resources are added to the list of resources for which the process is waiting. Okay, we need to classify that. Which resources are preempted, preemption or non-preemption, for example. Yeah. So process will be restarted only when it can regain its old resources, as well as the new one that it is requesting. And also for the circular wait, impose a total ordering of all resource type and require that each process requests resources in an increasing order of enumeration. So this can be used in practice. Yeah. Two bank transactions, 1 and 2. Yeah, when 1 and 2 execute concurrent. Transaction 1 transfer $25 from account A to B, and then transaction 2 transfer 50 from the same account. They say that here account B to account A. So this is the program. This is where we got this new tag. We use a lock. Okay, and then can see this, we need to apply the acquire lock and then acquire lock 2. Okay, we got 2 transactions right now. So withdraw, deposit, and release lock 2 and also 1. So this is that lock example with a lock ordering. Okay, all right. So ensure that the system will never enter that lock state. So what is the trivial way of avoiding deadlocks? Requires that the system to have some additional, a priori, called priori, priori. All right. Information available on possible resource requests. Yeah. So simplest and most useful model requires that each process declare the maximum number of resources of each type that it may need. Yeah. And then this algorithm, which is deadlock avoidance algorithm, dynamically examines the resource allocation state to ensure that there can never be circular with condition. Okay, so we need some inspection at the beginning. Yeah. So resource allocation state is defined by the number of available and allocated resources and the maximum demands of the process. So they need to know that also, yeah, to take account this kind of the things. Yeah. System is in a safe state if yeah, if what, if there is if there is a if there exists a sequence P1, P2, and Pn, which is representing all the processes in the system, that for each PI, the resources that PI can still request can be satisfied by currently available resource, including process resources held by all PJs, where with J must less than I. That is, if PI resource needs are not immediately available, of course, yeah, then PI can wait until all processes, which is PJ, all the process J mean all have finished executing. When they have finished executing, they release all their resources, then PI can start to obtain the needed resources, execute, yeah, return allocated resources, and finally terminate. When P terminates, yeah, PI can obtain its needed resources and so on so forth until finish all the processes. Okay. Regarding safe state, yeah, system is in a safe state if the system, yeah, if the system can allocate resources to each process up to maximum in some order, and still avoid the deadlock. Okay. If a system in a safe state means no deadlock will occur in future. So if a system is unsafe state means possibility of deadlock will occur in future. Yeah. So mostly this is the basic fact that we need to, accept that where deadlock is a unsafe is a unsafe scenario. Okay, and then the safe one is without the deadlock. Okay, so algorithm. So this is numbers algorithm that you just can go to the Google check. You can see a lot, yeah, thousand, but that could be different type of the application, but their purpose may be same, to avoid this deadlock. Yeah, so programmer basically will double check this. And not program researcher will always looking to produce new, techniques. They need to go through all the existing technique under the name or keyword deadlock avoidance in order for him or for them to create a new deadlock algorithm, deadlock avoidance algorithm. Okay, all right. So here all process can be started anytime when a process request for resource and algorithm is executed to check whether a deadlock may occur in future. Yeah. So if deadlock may occur, so the request is delayed. Okay. Right. So deadlock avoidance is to ensure that a system will never enter an unsafe state. Single instance of a resource type, use a variant of the resource allocation graph, and then for the multiple instances of resource type, use the banker's algorithm. So resource RAG scheme, yeah. All right. So we continue. All right. This okay later in the next following lecture. All right. Okay. Thank you.